Okay, here. So chapter 13, I don't know if I told you this, but you may have noticed that I've jumped from chapter 10 to chapter 13. And the reason why is because, in my opinion, the topic in chapter 13 is one that naturally follows from what we discussed in chapter 10, especially since we talked about, among other things, temperature as it relates to energy and so on. And temperature will become important also in chapter 13. So that's the reason why I've decided to go that route where we jump from chapter 10 to chapter 13, which deals with gases. All right. Whoops. What did I do? Okay, so gases. And I'm quite sure we're all familiar with the three states of matter: solid, liquid, and gas, right? And gases are a bit unique when compared to solids and liquids. And the main feature of gases which make them unique is that they respond dramatically to relatively small changes in temperature and also pressure, all right? The same cannot be said for solids and liquids. So for a relatively small, let's say, increase in temperature, what you'll find is that, and we're going to discuss this later on in one of the gas laws, you're going to find that for a small increase in temperature, the change in volume of the gas would increase dramatically. But if you were to apply this, the same extent in terms of the increase in temperature for solids and liquids, the level of expansion is not that great. So that's just one example of a big difference between gases, the way they behave, as opposed to solids and liquids, right? And what you're going to find, and we're going to discuss in this chapter, is the fact that there are laws which govern the behavior of gases, which do not apply to solids and liquids, all right? Now, at the heart of this topic is a theory which is used to explain all the gas laws that we're going to meet later on. And this theory is called the kinetic molecular theory, KMT for short, right? So there are certain assumptions that go with this theory. It's based on the fact that at the microscopic level, gases are made up of very small particles that are very energetic and always moving, right? And they move randomly, occasionally colliding with each other and colliding with the walls of the container that they're in, all right? Now, the gas that behaves exactly as described by the kinetic molecular theory, we call that an ideal gas, all right? Even though we give this definition of an ideal gas, in truth and in fact, there's no such thing, right? An ideal gas does not exist. However, a lot of the calculations involved based on the fact that gases behave ideally serves as a good approximation for understanding how gases behave, and we can actually do some calculations based on that, all right? So here are the assumptions of the kinetic molecular theory. The first one, as I said before, is that gases consist of very tiny particles. The second assumption is that the distance between the particles is large compared to the size of the particles themselves. The third assumption is that there's no forces of attraction that exist between the gas particles. The fourth assumption is that the gas particles move in straight lines in all directions, colliding frequently with one another and with the walls of the container. And no energy, this is the fifth one, no energy is lost when the gas collides with another particle or with the walls of the container. This. I think. Okay, so This fifth particular assumption, if I remember correctly from physics, it's called the conservation of, oh gosh, what's it called? Take that back. Basically what you're talking about is what we call an elastic property of these particles. Basically what this is suggesting is that when the particles collide with each other, let's say you have two molecules colliding with each other as gases, as a gas. So they have a certain amount of energy total between both of them. And after collision, energy is transferred from one to the other, all right? So basically what we're saying here is that you will have transfer of energy from one atom or from one particle to another, but the total amount of energy will be conserved. So therefore, the term that is used is that we say that the collisions are elastic, right? So that's basically what the fifth assumption is all about. So, the sixth assumption is that the average kinetic energy for particles is the same for all gases at the same temperature, and its value is directly proportional to the Kelvin temperature, all right? So basically, if you have two containers, let's say one contains oxygen, the other one contains nitrogen. If the temperature is the same for both of them, that means that the kinetic energy is the same for both of them, right? Now, what might be different would be the velocity, and this brings us to this equation right here. I don't know if you have met this before, but this is the equation for calculating the kinetic energy, which is the energy an object has by virtue of its motion. And come to think of it, we did meet this equation before in chapter 10, all right? Anyway, I think we did that. Anyway, so this is the equation that is used to calculate the kinetic energy, all right? So if you have two different gases, as I said before, nitrogen and oxygen, same temperature, they will be governed by the same equation right here, right? They will have the same energy. The difference between them, of course, is that the mass of the nitrogen and the mass of the oxygen will be different, which would mean that the velocity will be different. In fact, I think I have an example here. Right, well, before we get to the example, so because all gases have the same kinetic energy at the same temperature, that means that the result of that would be that the molecules that are lighter will move faster compared to the molecules that are heavier. So here's the example. Let's say you have hydrogen compared to oxygen, right? So the mass of hydrogen is 32 in terms of the molar mass or molecular mass, and the mass of oxygen is 30, the mass of hydrogen is 2, and the mass of oxygen is 32, right? So let me just include a little work here. So remember now, the equation I gave you was that the kinetic energy is equal to half mv squared, right? So if the kinetic energy is the same for both the hydrogen and oxygen in this case, that means that half the mass of oxygen times the velocity of oxygen squared will be equal to half the mass of hydrogen times the velocity of hydrogen squared, right? So if the halves cancel, you're going to end up with, what should I put this now? If I divide both sides by the velocity of O2 squared, and divide both sides by the mass of hydrogen, then this will cancel, and this will cancel. So this works out to be mass of oxygen divided by mass of hydrogen would be equal to the volume of hydrogen divided by the volume of oxygen squared, right? Now, the mass of oxygen is 32. The mass of hydrogen is 2. So this works out to be 16. So therefore, we can say that when we find the square root of both sides, we're going to end up with this equation right here, right? And what this equation tells you is that the volume, not the volume, the velocity of the hydrogen will be 4 times that of the velocity of the oxygen, which is to be expected because oxygen is heavier compared to the hydrogen, all right? So that shows you how the mass of the molecule is related to the velocity of the molecule at a particular temperature. All right, let me clear this here. Scroll down. Okay, one important concept that you need to understand when it comes to gases is the concept of pressure. And in everyday language, people tend to use pressure and force as if they mean the same thing, right? But they're two different things, even though they're related to each other. Force, let me talk about that first, is simply a push or pull, right? So if I push on something, anything, or I pull on it, I'm applying a force to it. Pressure is something different. Pressure is where you apply force over a particular area, all right? So as stated here, pressure is equal to force per unit area, and you can represent it mathematically this way. Pressure is equal to force divided by area. And therefore, the units of pressure can be expressed in terms of the units of force and area. The metric unit of force is Newton, and the metric unit of area is meter squared. So that means that the unit, based on this combination of units, the units of pressure would be newtons per meter squared. And there's a special name given to this combination of units. It's called the Pascal unit, all right? So that's basically one way, because there are other ways, but this is one way of expressing the unit of pressure. Let me clear this. So when it comes to pressure, we're going to look at the other units later on. But basically, when it comes to a gas exerting pressure, this model here basically explains it. As we said before, gas particles are always moving, always in random motion very quickly. Typically, their speeds would be about 300 meters per second. And therefore, they will be colliding with each other. But in terms of the pressure exerted, they will collide with the walls of the container, right? So if you can imagine literally billions of particles continually bombarding the walls of the container, what that would do is exert pressure on the inner walls of the container. So therefore, that's why, for example, a balloon, if it has gas in it, will remain inflated because you always have the continuous bombardment of the particles against the inner walls of the container. So that's basically explaining how a gas exerts pressure, right? Now, see this here. Turns out that the pressure exerted by a gas is dependent on a couple of things. One of them would be the number of gas molecules present. So therefore, everything being the same, if you increase the number of molecules present, if you pump some more gas molecules into a container, then the pressure would increase. The temperature of the gas would also have an influence as to the type of, or the amount of pressure exerted by the gas. And the volume also is very important in terms of a factor which would affect the pressure of the gas. So these are things that are governed by laws, which we're going to talk about shortly. Now, how do we measure the pressure of a gas? Well, firstly, I'm going to introduce to you this instrument here called a manometer. A manometer is basically an instrument that is used to measure the pressure of the atmosphere, right? As we all know, the air we breathe is a mixture of gases, right? The major component would be nitrogen, and then you have some others. Nitrogen is about just under 80% of the total air composition. And then the next in line in terms of composition would be oxygen, which is less than 20%, 19 point something percent. And then the rest would be other gases like xenon and so on, carbon dioxide, nitrogen, no, not nitrogen, carbon dioxide and so on. So basically, anything that exists within the atmosphere is subjected to the pressure exerted by the atmosphere. So basically, we can measure the atmospheric pressure. So this instrument here is called a barometer. Now, this is a very simple, unsophisticated version of it. It consists of a U-shaped tube. Not a U-shaped tube, a tube, which you would completely fill with mercury. And then you have a trough here, which has mercury in it. but this tube has to be long enough. It has to be at least 760 millimeters, right? And what you do is you'd use your thumb or index finger to cover the mouth of the tube. Of course, you should be wearing gloves for this because mercury is known as a neurotoxin. And then you invert it into the trough filled with mercury, and then you let it stand for a while. And what will happen is that the mercury level will fall to about 760 millimeters above the surface of the mercury in the trough, right? And it turns out that basically the reason why this mercury column is supported up to this height is because you have atmospheric pressure acting on the surface of the mercury outside the tube in the trough, right? So if weather conditions change and the atmospheric pressure increases, let's say, for example, it increases, then what will happen is that the atmospheric pressure acting here will force the mercury level to go higher. If the atmospheric pressure decreases, then the opposite is going to happen. And therefore, as a result, the height of the mercury column here is used as a measure of the magnitude of the atmospheric pressure, right? And this leads us to another unit of pressure, which is called millimeter mercury, right? Which is shown right here, right? So by definition, we have what is called the atmosphere unit, which is presumably the pressure exerted by the atmosphere, right? So by definition, and this has been defined by the powers that be, by definition, 1 atmosphere is equal to 760 millimeters mercury, which would be the height of the mercury column in the setup I just showed you, all right? There's another unit known as the Torr unit, which is basically the same as a millimeter mercury unit. The Torr unit is named after a very important Italian physicist known as Torricelli. So 1 torr is the same thing as 1 millimeter mercury. And there's some other units here. There is I mentioned the Pascal unit earlier, right? Well, this is the kilopascal. Kilo means 10 to the 3. So 1 kilopascal is equal to 1,000 pascals, right? So 1 atmosphere turns out to be equal to 101.325 kilopascals. And then there's some other units here, which, to be perfectly honest, I don't anticipate us using, but they're used in different fields and so on, all right? So that's the relationship between the atmosphere unit here and the millimeter mercury unit, the Torr unit, and the kilopascal unit, all right? Okay, so this is just giving you some data concerning dry air. As I mentioned before, most of the composition of air is nitrogen, 78.08%, and then oxygen is 20.95%. So I was a bit incorrect when I said just under 20%. It's just above 20%. And then you have some other gases like argon, carbon dioxide, neon, and so on, all right? Okay, let's talk about the relationship between the pressure of a gas and the number of molecules and the temperature, right? So as we said before, the pressure that a gas exerts is a manifestation of the continuous bombardment of the walls of the container by the molecules colliding with it, right? So as stated here, at a specific temperature and volume, the number of collisions is dependent on the number of gas molecules, right? So basically what you'll find is that the number of collisions would be, of course, directly proportional to the number of gas molecules present, which would be proportional to the pressure exerted. And I think that's what this diagram here is illustrating. So here we have some representations here for hydrogen, right, 1 mole. Here we have 2 moles of hydrogen, and here we have half a mole of hydrogen, right? And these are all at the same temperature and volume. The volume is 22.4 liters, the temperature is 0 degrees Celsius. So, sorry about that. So basically, if you double the number of moles from 1 to 2, then the pressure will be doubled from 1 to 2, right? If you halve the number of moles from 1 to 0.5, then similarly, the pressure would be half from 1 atmosphere to 0.5 atmospheres, right? Now, the next diagram down here is showing you, giving you information about the number of molecules. And we're all familiar with Avogadro's number, which represents, in this case, the number of molecules present in 1 mole of hydrogen. So again, the pressure will still be 1 atmosphere. And here we have 1 mole of oxygen, right? And the pressure is 1 atmosphere, right? And then if you were to combine these two together, then basically where you have half moles of hydrogen and half moles of oxygen, right? The total number of moles would be 1 mole and the pressure would still be 1 atmosphere, right? So what this indicates is that it doesn't matter the nature of the gas. It could be hydrogen, it could be oxygen, it could be whatever. The important thing you need to recognize is the relationship between the pressure and the number of gas molecules. It's a proportional relationship, all right? And it doesn't matter what the gas is, as long as the volume and temperature are the same, then the pressure exerted by the gas would be the same for the same number of moles. Okay, temperature dependence. Let me go through this quickly. So I'm quite sure we're all familiar with the fact that for any gas, if you were to increase the temperature, its pressure would increase, right? And we can again explain that based on the kinetic molecular theory, right? Basically, when you increase the temperature of a gas, basically you're giving or imparting energy to the gas molecules. So the gas molecules will have more kinetic energy, which means that the molecules will hit the walls of the container more frequently and with greater force. And as a result, the pressure of the gas would increase accordingly. And that is demonstrated in this diagram right here. Here we have a gas. I'm not sure what the gas is. Doesn't matter anyway. They gave it temperature, they gave it volume, they gave it moles, and they gave it pressure, right? And then you increase the temperature from 0 degrees Celsius to 100 degrees Celsius. Everything else remains the same, excepting, of course, the pressure. The pressure will increase from 2.24 atmospheres to 3.06 atmospheres, right? So that shows you or demonstrates the relationship between the pressure and the gas. And again, as I said before, we can explain that based on the fact that by increasing the temperature, the molecules will gain more kinetic energy, will hit the walls of the container harder with greater force, and therefore that leads to a greater pressure exerted. So to summarize, the lower the temperature, the lower the pressure exerted by the gas, the higher the temperature, the higher the pressure exerted by the gas. Okay, so this is what I was hastening to get to, the first law that we're going to discuss. So there are several laws that govern the behavior of gases, right? The first of which is Boyle's law. And Boyle's law says, in words, at a constant temperature and volume, at a constant temperature, the volume of a fixed mass of gas is inversely proportional to the pressure, all right? So one way of stating that law is what you see here. I don't know if you're familiar with this sign right here. This sign means proportional to, right? So basically what this is saying is that the volume of the gas is proportional to 1 over the pressure, right? So basically what that law is saying, and I'm quite sure you know this from your everyday experience with any gas, right? What this law is saying is that if you were to reduce the volume, then the pressure of that gas would increase proportionally, right? As long as the temperature and the amount of gas is fixed, right? So if you were to, let's say, halve the volume of the gas, then the pressure of the gas would be doubled, right? If you were to reduce the volume of the gas by 1/3, then the pressure of the gas would triple and so on, all right? So that's basically what this law is saying. Another way of stating this law, which is more useful, especially for the type of problems that we're going to do, is this right here. In fact, let me just add a little thing right here. So there's one way of expressing this law, which I don't have here in this PowerPoint, and that is that, let me do it here. V is equal to K times 1 over P, right? Where K is a constant, right? And then we can rearrange this to get PV is equal to a constant. So what this is saying is that it doesn't matter what the pressure and volumes are, as long as the temperature and the amount of gas is fixed, when you multiply the pressure times the volume, it's equal to a constant value, right? And for those of you, if you plan to enroll in my Chem 1 class, Chem 1 lab class, there's an experiment which beautifully demonstrates this particular Boyle's law, which I just conducted with my students in my current Chem 1 lab class this past week, or this week actually, right? And the data basically shows you what this is saying, that P times V is equal to a constant, right? Now, based on this, we can come to the conclusion that this is true. So what does this say? This is saying that if you have an initial pressure P1 and an initial volume V1, right? And then you change the pressure from P1 to P2 and change the volume from V1 to V2, then P1 V1 is equal to P2 V2, right? So basically, this equation here is useful because if you know any three of these terms, you can rearrange it to get the fourth term, right? And that is what you're going to see, in fact, in the assignment, the first couple of questions in the assignment that we're about to do, okay? So these are just different ways of stating Boyle's law. Now, this here is a graphical demonstration of Boyle's law again. And in fact, this graph is also from the experiment that I just did with my students, they actually plotted this graph and basically they get the same shape. This is a plot of pressure on the y-axis versus volume on the x-axis. And as you can see, as depending on where you're going to start, if we start here, where the volume is relatively large, right, and you reduce the volume, you notice that the curve goes up, which indicates that the pressure is correspondingly increasing, all right? So that's just a graphical way that shows you pictorially the relationship between pressure and volume. And this is a diagram here which basically shows you again the relationship, this time showing you that PV is equal to a constant. So here we have a gas trapped in this container where the volume is 1,000 mils and the pressure exerted is 1 atmosphere by the gas. And let's say all of a sudden you increase or double the pressure of the gas from 1 atmosphere to 2 atmospheres, the volume would be halved as a result. But guess what? P times V, 2 times 500, is equal to 1 times 1,000. So that shows you that PV is constant. And then if you take it further where you reduce, or I should say double the pressure more from 2 to 4 atmospheres, the volume will correspondingly decrease by 2 to 250 mils. And then when you multiply the pressure times the volume, that is the same as 1,000, which is what you calculated here and here. So basically, this is just basically demonstrating that the pressure times the volume will be constant. But again, you need to remember that this is only true if the temperature, T, and the amount of gas is constant. N is used to represent the number of moles, which is the amount of gas, right? So those two factors would have to be held fixed in order for you to see Boyle's law working this way. Okay, so here's an example. It says an 8-liter sample of nitrogen is at a pressure of 500 torr. What must be the pressure to change the volume to 3.00 liters? And it says here that the temperature is constant. So of course, Boyle's law is what we're going to use here. So whenever you're given questions of this type, it's very important that you read the question carefully so you can identify what is P1, what is V1, what is P2, and what is V2, right? So Boyle's law is P1 V1 is equal to P2 V2, right? So based on the information provided, I would say that, well, firstly, what the question is asking for? The question is asking for the pressure, right? They gave you the initial volume, they gave you the initial pressure, and they gave you the final volume. So basically, we need to find the final pressure, which is P2. So if you divide both sides by V2, you're going to get P2 is equal to P1 V1 over V2. And we put P1 as 500 torr times V1, which is the initial volume, 8.00 liters, divided by V2, which is 3.00 liters. And then we do the calculation. So that's 500 times 8 divided by 3. Oh, okay, I just realized something. I'm going to let this be 500 with a decimal point here. So the number of sig figs here would be 3, so that would be 133 torr. And that's it. And that's how you do that. All right? Any questions about this one? Any questions about this example? Any questions? Okay, so let me clear this here. And I think I may have don't have any other examples. So let me get you started on this assignment. Before we move on to Charles' law. There you go, sir. Okay, and I think for you guys out there in Zoom, I think I have already published assignment number 13, but let me check just to make sure. Let me go here, let me go here, let me go. Okay, so yes, it's published, right? So you guys out there in Zoom, you can go ahead and download assignment number 13. And we're going to start with what I've done in this particular assignment is that I've divided the questions under the different topics. All right, so I'm going to start off with Boyle's Law first, and then we'll move on to the other laws, right? Okay, so the first question says, if I have 5.6 liters of gas in a piston at a pressure of 1.5 atmospheres and compress the gas until its volume is 4.8 liters, what will be the new pressure inside the piston be? All right, so remember now, Boyle's law says P1 V1 is equal to P2 V2, right? Okay, so based on the information provided in the question, what would you say P1 is? 1.5 atmospheres. So that's P1. What is V1? Sure about that? 5.6. Because 4.8 would be V2. You're starting from 5.6, you're ending up with 4.8, right? So P2 is what you're asked for, right? So as we said in the example that I showed you, P2 is equal to P1 V1 over V2. And then we put the numbers in. So P1 is 1.5 atmospheres. V1 is 5.6 liters. And V2 is 4.8 liters. And then we do the number crunching. So 1.5 times 5.6 divided by 4.8. And according to my calculation, the answer is 1.8, rounded off to 2 sig figs. And because the liters units cancel out, the final units would be 1.8 atmospheres. Yes, ma'am.
1.7, will that still be right, or would
It would be,
if I put
it would be slightly incorrect. Because what I got when I did this on my calculator, I got 1.75. And because I know that I had to round it off to 2 sig figs, when you round off 1.75 to 2 sig figs, it's 1.8, according to the rules of rounding off. Right? If the digit after the 7 is 5 or greater, that means that you have to increase that digit by 1.
So does that mean that we will always have to round up?
Yes, because you have to express the final answer to the correct level of precision, which means that you have to round off your answer to the correct number of either sig figs or decimal places, depending on whether you're adding, subtracting, multiplying, or dividing. One additional thing I want to say here about the use of Boyle's law, excuse me, is that it does not matter what the units that you use for pressure and volume, right? As long as they're the same on both sides, right? So whatever the units for P1 is, you have to use the same units for P2, all right? And the same is also true for the volume units, right? Whatever the units that you use for V1 must be the same as the units for V2. And the reason why I mentioned that is because, and I'm not sure if I give an example in this assignment, but, excuse me, you could be given a question where, let's say the volume is given in liters for V1, and for V2, it is given in milliliters, right? But you have to use Boyle's law. In that particular case, what you'd have to do is, you'd have to either convert the milliliter unit to the liter unit and then put a number in Boyle's law, or the other way around, convert the liter value to milliliters or milliliter value to liters, as long as the units end up being the same on both sides, right? So that's one important thing that you need to recognize about Boyle's law. It doesn't matter what the units you use, as long as they're the same for the same type of terms on both sides of the equation. Okay, any questions or any other questions about this question right here? Any other questions? Yes, ma'am.
So for the rounding part,
Mm.
is that as long as you can round up? Because let's say that it would have been 1.4, it's just an example. You don't have to round up, you just put 1.4.
Well, it depends on the type of calculation that you did to get 1.4. Because, okay, let me explain using this example. You'll notice that in this example here, on this side of the equation, right? You have 1.5, 5.6, 4.8, right? Those are all 2 sig figs. those are all expressed to 2 sig figs. So even though when I did the calculation on my calculator, I got 1.75, I have to round the answer off to 2 sig figs, because according to the rules that we learned earlier, whenever you're dividing and or multiplying, you round off your answer to the lowest number of significant figures, right? So in this case here, they're all 2 sig figs, so therefore that means that you round off your answer to 2 sig figs, right? Now, if you had a situation where the lowest number of sig figs was 1, right? And you got 1.4 when you did the calculation, right? That means you have to round off the 1.4 to 1. Because the lowest number of sig figs involved in the calculation was 1 sig fig. So you have to round off 1.4 to 1 sig fig, which is 1, basically, right? So it all depends on the numbers. It all depends on the number of sig figs of the numbers involved in the calculation. That's basically what it comes down to. All right? Okay, any other questions before we move on to question number 2? Any other questions? All right, so let me clear this and scroll down. Okay, let me hear what you guys have to say about number 2. Number 2, they said that a gas occupies 12.3 liters at a pressure of 40.0 millimeters mercury. What is, and there's a typo here, that should be the volume when the pressure is increased to 60.0 millimeters mercury. Okay, so let me hear what you guys have to say about this one. Let me remind you that the equation you're going to use is P1 V1 is equal to P2 V2. All right. So let me hear what is, and the question is asking for P2, right? So that's P1 V1 over V2. So what is P1 in this question? Yes, ma'am.
Says what is the volume?
I'm sorry, the volume. Thank you. My bad. Volume. So that would be V2 is equal to P1 V1 over P2. Thank you. Okay, so what is P1 in this case? 40.0 millimeters mercury. And what is V2? 12.3 liters. And what is P2? 60.0 millimeters mercury. Exactly. Okay. So let's do the number crunching. 40 times 12.3 divided by 60. And according to my calculation, now this is another interesting, to go along with some of the questions that you have been asking. This is another interesting significant figure type of issue, because here we have 3 sig figs here, 3 sig figs here, 3 sig figs here. When I did the calculation, this is what I got. I got 8.2, right? But because these are all 3 sig figs, I have to add a 0 here to make that 3 sig figs, right? So the answer is actually 8.20 liters. These units will cancel out, and therefore, my throat is acting up again. And therefore, you get that answer being expressed to 3 sig figs. All right? Any questions about this one? Any questions? Okay, very good. Let me clear this. Number 3. Okay, it says if a gas at 25 degrees Celsius occupies 3.60 liters at a pressure of 1.00, another typo here, this should be atmospheres. What will be its volume at a pressure of 2.50 atmospheres? Okay, so again, P1 V1 is equal to P2 V2. What's the question asking for? The volume, V2, which would be equal to P1 V1 over P2. So what is P1? 1.00 atmospheres. What is V1? 3.60 liters, all divided by P2, which is 2.50 atmospheres. So let's see what that gives. Okay, so according to my calculation, this works out to be equal to 1.44, and the units will be liters because the atmosphere units will cancel out here and here. And that's it. All right? That's how that is done. All right. Any questions about this one? Any questions? Questions? Okay, I'm going to leave the rest in that section for you to do on your own because I want to get to at least Charles' law and maybe some other, and maybe Gay-Lussac's law after. So I want you to attempt on your own questions 4, 5, 6 under the Boyle's law section. All right? Okay. So going back to the PowerPoint now, we're going to talk about Charles' law, which is another law which talks about the relationship between the volume of a gas and its temperature. And Charles' law came about as a result of observing what happens to the volume when you reduce the temperature of a gas, right? So this is a graph showing you what happens when you do that. You see that the volume of the gas, oh, by the way, this is a plot of volume versus temperature in degrees Celsius, right? And what is observed is that as you reduce the volume of the gas, as you reduce the temperature of the gas, the volume decreases. Now it gets to a point, of course, as we all know, is that when you cool a gas to a sufficiently low temperature, it converts from gas to liquid, right? So when it comes to liquid being formed, you cannot measure the volume. Well, the volume doesn't really, not important. Well, the volume cannot be used, let's put it that way, because now it's not a gas, it's a liquid. So after below the boiling point, let's put it that way, you cannot establish a relationship between the volume of the gas and the temperature of the gas because now the gas will be a liquid. So what was done, since we cannot measure the volume of a gas below the boiling point, what was done was that they extended this line here to cut the x-axis, which basically indicates what the volume would be and what the temperature would be when it cuts the x-axis if the gas were a gas below that temperature. But of course, we know it's not a gas, right? And it turns out that this point here, when the temperature is expressed in degrees Celsius on the x-axis, this line will cut it at this value here, minus 273 degrees Celsius, all right? And what this seems to suggest is that if the gas were to exist as a gas at those low temperatures, then its volume would contract to zero at that temperature, all right? In other words, basically the particles will have no kinetic energy whatsoever, all right? So basically, this actually is the reason why we now have the Kelvin scale, because what they decided to do in order to establish the Kelvin scale is they say that, okay, since the axis here is cut by the line at minus 273 degrees Celsius, then this is defined as 0 Kelvin, all right? So therefore, minus 273 degrees Celsius is equal to 0 Kelvin. And in fact, the relationship between the Kelvin scale and the Celsius scale is this right here. Temperature in Kelvin is equal to the Celsius temperature plus 273, all right? So this is the relationship between the Kelvin scale and the Celsius scale based on the behavior of gases as demonstrated in this graph. Excuse me. All right, so that brings us now to Charles' law, which says, here it is, that the volume of a gas, the volume of a fixed mass of gas is directly proportional to the temperature expressed in Kelvin, or the absolute temperature, all right? So this can be expressed in several ways. It can be expressed like this, which says that the volume is directly proportional to the temperature. It can also be expressed in this way, V1 over T1 is equal to V2 over T2, all right? Now, as I said before, in relation to Boyle's law, it doesn't matter what the volume units are as long as they're the same on both sides. However, when it comes to the temperature part of this equation, the temperature must be expressed in Kelvin, right? Temperature must be expressed in Kelvin. So in other words, if you're given a problem where the temperature is given in degrees Celsius and you have to use this equation, you have to first convert to Kelvin by adding 273, and then you plug the numbers into that equation to solve for whatever the question is asking for. All right? Okay, so that's Charles' law, basically. So this is showing you the effect. Oh, right. So basically, you have a container here with a gas, And the pressure is constant, right? But you increase the temperature from T1 to T2. And this is all hypothetical, of course. If you imagine having a free floating piston, it moves freely, then what will happen is that the volume will increase accordingly, right? And that is due to, of course, the increased temperature. Okay, so let's look at this example. It says a 255 ml sample of nitrogen at 75 degrees Celsius is confined at a pressure of 3.0 atmospheres. If the pressure remains constant, what will be the volume of the nitrogen if its temperature is raised to 250 degrees Celsius? So it is the equation that we're going to use, of course, is V1 over T1 is equal to V2 over T2. So again, when it comes to these questions, you have to read it carefully to identify the different terms, right? So the question is asking for the volume when the temperature is increased, right? So the question is asking for V2. So what I would do is rearrange this to get V2 is equal to V1 over T1 times T2. And the way we get that is that we simply multiply both sides by T2, right? So that this T2 will cancel out with that T2. So V2 will be equal to V1 over T1 times T2, all right? So V1 is the initial volume of the gas, which is 255 mils, times T2. Now T2 is 75 degrees. We have to convert the 75 degrees to Kelvin. So we have to add 273, 75 plus 273. So that's 348 Kelvin, all right? So that goes here, 348 Kelvin. And then we divide by T2. Now T2, so this is T1. T2 would be equal to 250 plus 273. And that would be equal to 523. So that's 523 Kelvin. And that's it. So we put the numbers in, 255 times 348 divided by 523. So according to my, okay, so how many sig figs here? 3 sig figs, so that's 170 with a decimal point here. And the units will be mils. And that's it.
To get 273.
How did I get, the 273? That's what you do, that's what you add to the value in Celsius to convert it to Kelvin.
Okay.
Right. So whenever you have to convert from Celsius to Kelvin, you add 273. If you have to do the reverse, convert from Kelvin to Celsius, you subtract 273. All right. Okay. Any other questions? Any other questions? Any other questions? Okay. Okay. So again, assignments. This time we're going to look at the Charles Law questions, starting with number 1. So remember now, the law that we'll be using in this case, in this section, is V1 over T1 is equal to V2 over T2. All right? Let's go. So this question says that the initial temperature is 4 degrees Celsius, the final temperature is 22 degrees Celsius, and the final temperature is 4 degrees Celsius. The initial temperature is 22 degrees Celsius, and the initial volume is 0.50 liters, all right? So, and the question is asking for the final volume, V2, right? So V2 would be equal to V1 over T1 times T2. So what would be V1 in this question? Yes, ma'am.
It will be 22 Celsius, but if you do, like, if you convert it, it's gonna be.
Oh, so, okay, hold on. Okay, I didn't ask that, but since you went there, yeah, you have to convert the Celsius value to Kelvin, all right? So we can do that now. So what would you do to convert this to Kelvin?
273.
All right, so 273 plus 4 gives you what? 277, right?
What's T2?
Hmm?
I mean, it'll be 277.
Yeah.
Yeah.
So that's T1. What about T2? So that's 273 plus 22 gives you what? Oh, I did something wrong here. 273 plus 22 gives you what? 295. So 295 Kelvin would be T2. All right. So I was asking, what would be V2? The volume. I'm sorry, what would be V1? I'm sorry. The initial volume. 0.50 liters multiplied by T2, which we calculated here to be 295 Kelvin, and then we divide by T1, which is 277 Kelvin. 0.5 times 295 divided by 277. Okay, so according to my calculation, this works out to, when rounded off to 2 sig figs, 0.53 liters, because the kelvins will cancel out here and here. Yes, ma'am.
So how come T1 is not 295?
Because of how the question is worded. Because the question says the temperature inside my refrigerator is about 4 degrees Celsius, right? Then it says, if I place a balloon in my fridge that initially has a temperature of 22 degrees, so that will be T1, initially, right? And a volume of 0.50 liters, so that will be V1, right? So the initial temperature and the initial volume would be 22 degrees, which is 295, which is T1, and 0.50 liters, which is V1, right? So you have to pay attention to how the question is worded, right? And then it says, what would be the volume when it is fully cooled by my refrigerator? So 4 degrees would be T2, which is the 277.
Wait, so, but you put T1
Yeah.
as 277.
I did?
Yeah.
T2, oh yeah, you're right. Okay, so T2 should be 295. Thank you.
No, T2 should be 277. Right, because it's 4 Celsius.
No,
Mm-hmm.
again, it goes back to how the question is worded.
But you said that initially the temperature is 22 Celsius. So that's T1.
Yeah.
Oh yeah, you're right.
For the last
Yeah,
one,
okay, bye-bye.
T1 was initially.
Yeah, thank you. Yeah, okay, that's what you're saying, yeah. So this should be T1. My bad. So 295 should go here. And T2 would be 277. Okay, which should make sense. Because the volume should be less, not greater, times 277 divided by 295. Okay, thank you for pointing that out. So the actual answer is 0.47. The volume should be less because it's being cooled. Okay. Um, 0.477 liters. All right, thank you very much for pointing out that error on my part. Okay, any other questions about this? Any other questions? Okay, let me clear this. And let's look at this here. Let me hear what you have to say about this one. What's the question asking for? Okay, so it's asking for V2, right? Which would be equal to V1 over T1 times T2. Okay, so what is V1? 0.40. What is T2? Exactly, this would be T2, but you have to convert it to Kelvin. So 250 plus 273 That gives you 523 Kelvin. All right, and so that goes here, 523 Kelvin. And then what is T1? Exactly. So that goes down here. Okay, so let's see what that gives. So according to my calculation, this works out to be equal to 0.713, I'm sorry, 0.714 liters. All right. Okay, so that's that. Now, the next law we're going to look at, and this is probably the final law that we're going to look at today, clear this here, is Gay-Lussac's law. And Gay-Lussac's law deals with what happens, it deals with the relationship between pressure and temperature of a gas. So basically, this is Gay-Lussac's law in words. The pressure of a fixed amount of gas at a constant volume is directly proportional to its Kelvin temperature. One way of stating that is P is equal to KT, all right? Another way of stating that is P1 over T1 divided by P2 over T2. So this is very similar to the Charles law that we saw earlier. The only difference is that the pressure terms are replacing the volume terms. And again, as in the case of Boyle's law, it doesn't matter what the units are for P1 and P2 as long as they're the same. But again, the temperature units must be Kelvin, right? Wherever you see temperature in any gas laws, from this law to any law that we're going to encounter in the future, the temperature must be expressed in Kelvin. So let's look at this example right here. This question says, it gives you the initial temperature, it gives you the initial pressure, and it gives you the temperature afterwards. And the question is asking for the pressure, right? So the equation is P1 over T1 is equal to P2 over T2, right? So the question is asking for P2, which is equal to P1 over T1 times T2. So P2 would be equal to the initial pressure, which is given as 2.15 atmospheres, times the final temperature, which is 100 degrees Celsius, which you have to convert to Kelvin, which means that you add 273 to 100, which is 373 Kelvin. And then we divide that by T1, which is the initial temperature, which is 40 degrees plus 273, and that gives 313 Kelvin. So that's a setup. So 2.15 times 373 divided by 313. And according to my calculation, this works out to be equal to 2.56. The Kelvin units will cancel out, so you're left with atmospheres. And that's it. That's how you do that. So it's very similar to what we're doing in the examples, the Charles law examples that we looked at earlier. All right? Any questions about this example? Any questions? Any questions? Okay. So let's go to the assignment again. So this question, number one, is asking for you to determine the pressure change when a constant volume of gas at 1.00 atmospheres is heated from 20.0 degrees Celsius to 30.0 degrees Celsius. So this question is asking for the change in pressure, right? And the change in pressure would, of course, be the difference between the final pressure and the initial pressure. So change in pressure would be equal to P2 minus P1. So basically what we need to do is find P2 and P1 first, and then find the difference between them to get the change in pressure. So remember now, the equation is P1. Well, actually they gave you P1 already, which is 1.0 atmospheres. Anyway, P1 over P2 is equal to, I'm sorry, P1 over T1 is equal to P2 over T2, all right? So what I would do is try to find P2. So P2 would be equal to P1 over T1 times T2, all right? So P1 is 1.00 atmospheres. T2 is the final temperature, which is 273 plus 30, that gives you 303 Kelvin, all right? And then we divide that by T1, which is 293 Kelvin, because that's 20 degrees Celsius. Excuse me. So let's see what that gives. 303 divided by 293. So I got 1.03 atmospheres. Thanks. So that is P2. Now remember, what the question is asking for is the change in pressure. So therefore, as I said before, the change in pressure is P2, which is 1.03 atmospheres, minus P1, which is given in the question as 1.00 atmospheres. That would give you 0.03 atmospheres. And that's it. All right. Any questions about this one? Any questions? Okay. Let me clear this. Okay. So in this case, in this question, it says if a glass in a closed container, if a gas, I'm sorry, in a closed container is pressurized from 15 atmospheres to 16 atmospheres, and the original temperature is 25 degrees Celsius, what will be the final temperature is? B, right? So again, it's P1 over T1 is equal to P2 over T2. Now, the question is asking for the final temperature, right? In other words, it's asking for T2, right? So this begs the question, how do we solve for P2 from here, right? Well, one thing you could do is cross multiply. I'm quite sure you're familiar with that from your previous math courses. If you cross multiply, you're going to get P1 T2 is equal to P2 T1, right? And then now to get T2 by itself, we divide both sides by P1, right? So that will cancel with that. So you're going to end up with T2, which is what the question is asking for, is equal to P2 T1 over P1. And then we plug the numbers in. So we have to identify what is P2, what is P1, what is T1 from the question. So P1 would be the 15 atmospheres, P2 would be the 16.0 atmospheres, and T1 would be 25 degrees, which when converted to Kelvin would be 298 Kelvin when you add 273, all right? So we put the numbers in. P2 is 16.0 atmospheres times T1, which is 298 Kelvin, all divided by P1, which is 15.0 atmospheres. So let's see what this gives. 16 times 298 divided by 15. And according to my calculation, this works out to be equal to 380 Kelvin. And that's how you do that. All right? Any questions about this one? Any questions? Questions? All right, so I'm going to leave number 3 for you to do. Let me see here. 3 and number 4, all right? And we'll have to stop here because it's now 10:41. But before you leave, let me just say that I have published, let me check to make sure I've done that, but I think I've published the videos for this chapter, chapter 13. Let me just check and make sure. Okay, so it's published, right? So far, we have covered these 2 first videos. You can rewatch them if you want to. That's up to you. But I want you to watch the rest of these in preparation for the rest of the questions. So we're going to continue discussing excuse me, discussing this assignment next week, right? But make sure you watch the videos for that. for the rest of the chapter, all right? And of course, your test is in the testing center. Today is supposed to be the last day, but I've been getting some messages from students, not only from this class, other classes, that they're not able to schedule an appointment because all the slots are filled. If you're one of those students, send me an email as soon as possible so that we can make arrangements for you to do the test, right? So more than likely, you'd have to do the test during my office hours. So if you're one of those students, all right? So if you find yourself not being able to get a slot from the testing center, please email me ASAP, all right? And by the way, I'll be, well, not in my office, I'll be in the adjunct office over in Building 7 today from 2 to 5, if you have any, questions, whatever. All right? All right, folks, so that's it for today. See you all next week. Okay. Mm.
I scheduled the project for us, and then not to be on us.
Okay, no problem.
So.
Yeah, that's fine, that's fine.
What about you know? I didn't say, I don't think I said it right, on the campus too.
About,
I'm Shivani, by the way.
okay, what, I
was
don't have
about-
any emails that were.
Okay, sorry,
Yeah.
it was about I was talking about the.
Oh, okay. Let me see here. I made a note of. All students don't have the same issue. What's your last name?
Patterson.
Okay, what was the issue with the first test?
They had just told me that it was sent to you.
Okay, so this is CHM 925 section, section principle.
This section,
Okay, and
it was the first test,
where did you do the test number 1? Where did you do the test?
the test,
I mean, which campus?
this one.
Okay, okay. All right, so I'm going to try to track that down,
Okay,
because
cause they told me that they sent it to you, so I don't know.
well, if they did, that means I should have it. So I'll track it down.
Okay. And,
So you should get an email from me, later today.
okay, and the test that I just took.
Okay.
I had a couple questions,
About it.
yes,
Well, I don't have a copy of the test here. You remember?
yeah.
You're the one
I
who,
was the
hold on.
Yeah.
I think I remember now. You're the one who, oh, you know what? Let me close this for this. You guys out there in Zoom,